welcome to Classical Mechanics 2. In this video, we'll be discussing conservation of energy and conservative forces. First, we'll define what conservative forces are, and then we'll look at what it means for the dynamics of a system to come from its energy landscape. Let's start with the work-energy principle. This says that the change in kinetic energy of a system is equal to the net work done on that system. Here, work is defined as the integral along some path from point R1 to R2 of the force acting on that system dotted into the differential path element. Energy is conserved in a system when no net work has been done on it. Imagine we have a system and it has some forces in it, and we want to move a particle from point R1 to point R2 along some path. For example, this path here. So I want to know if the work is the same when it's done along this path or along this straight path here. If the work on that particle does not depend on whether I took the circuitous path or the direct path, we say that the force is conservative. When the force is conservative, then we can use the work-energy principle to define something called a potential energy. When no external work is done on a conservative system, the total energy doesn't change. We can invert the definition of work to say that force is equal to minus the gradient of our potential energy. Let's look at this a little bit more formally. Here I have the same system as I did before. I'm going to move my particle from point R1 to point R2 along this path, and then back from R2 to R1 along this path. If our force is conservative, we know that the integral along this path of force dotted into the path length is equal to 0. Since this is a closed path, it can also be the boundary of a surface S. This surface has a normal and an area element, dA. We can use this to reframe our work-energy theorem in terms of Stoke's theorem. So Stoke's theorem states that the integral along some closed loop gamma of some field f dotted into dr is equal to the integral across a surface bounded by that path gamma of the curl of f dotted into the area element of the surface dA. If the force is conservative, then the net work along this closed path is equal to 0. That means that this integral over here is 0. And this leads us to a condition on our force. A force is conservative if the curl of the force is equal to 0. This is consistent with our work-energy principle. If our force vector is given by the gradient of a scalar function, it necessarily has 0 curl. We can use our definition of potential energy to describe the mechanics of many systems. Physicists often like to think about potential energy as some sort of landscape with hills and valleys in it. Sometimes this might be a very high-dimensional set of hills and valleys, but we'll start with a 1D example. Imagine I have a particle living in this potential energy landscape. The total energy in the system is fixed, and our particle is now confined to live in this basin here. So what does its dynamics look like? Since it's trapped near the bottom of this well, let's Taylor expand the energy about its minimum at x0. We get that the potential energy is approximately equal to the potential energy at x0 times u prime of x0, which is necessarily 0 because we're at a local minimum, times x minus x0, plus 1/2 u double prime at x0 times x minus x0 squared, plus higher order terms. So let's rewrite the energy near the minimum, keeping only the constant and quadratic terms. This gives us locally parabolic behavior about x0. So if I were to take minus the gradient of this potential, I'd get an approximation for the force acting on the particle in this well. And that force is going to be minus u double prime of x0 times x minus x0. And this is equal to mass times the acceleration of the particle. So this is really just the equation for the simple harmonic oscillator. The force is proportional to the distance away from x0 that it has moved. So a particle will oscillate about point x0 with some frequency that's given by the square root of u double prime at x0 divided by m. In the next video, we'll use conservation of momentum to study how systems with variable mass, like rockets, behave. Thanks for watching, and I'll see you next time.